Okay, so all right, guys. So thanks a lot for being here. And today we are very happy to have Wenbo here to give a talk. So Wenbo is now a postdoc associated at UC Berkeley, working with Professor Dong Song, and he will be joining the Purdue University as an assistant professor this year. And his research interests are machine learning and cybersecurity. His work includes strengthening the fundamental property of machine learning models and design customized machine learning models to handle security unique challenges. And he's a recipient of multiple prestigious awards, including the IBM PhD Fellowship and ACM CCS Outstanding Paper Award in 2018. So today he's going to talk about strengthening and enriching machine learning for cybersecurity. Thank you so much. And Wenbo, the floor is yours. Please go ahead.
Sure. Thank you. Yeah, thank you so much for the very nice introduction. And thank you very much for inviting me. So this actually is kind of like this slide was migrated from my academic job talk. So it contains most of my work, kind of my vision. I have been thinking about for years in the field of machine learning and cybersecurity. So basically, in this slide, I'm gonna briefly talk about why machine learning fails in cybersecurity and the future directions that we can potentially make it work. Of course, with the recent kind of like a development of all those large language models. So how can we incorporate those success in traditional machine learning application domains to security applications. So before I get started, I just want to acknowledge my great colleagues from all these institutes and companies. This research cannot be done without their help. First, I give a few slides of motivation, but I feel for most of you here should be very familiar with all these things, right? So basically, the first, I think the motivation of we use machine learning in security is like sometimes many security applications such as malware classification, intrusion detection, they require a lot of domain experts. But like we have like millions or even trillions number of bugs like happening every day, right? So we in security domain we are facing a workforce shortage. Which means that we have limited number of security experts to deal with all the security events that happens daily. So to battle against this workforce shortage, our community recently started to use AI, which is artificial intelligence and advanced AI machine learning techniques, deep learning, all those techniques to help us make some of the security analysis step more automatic, which means we can just release human workforce and make security solution more skilled. So we actually have done pretty well. We can see there's so many products coming out, so many security companies that are flying because of AI. But there are always a downside of a story. So basically, here we can study, okay, why, what are the problems here, right? So the first thing is like, it's very common, like it's also very well known. It's like existing machine learning techniques lack the guarantee of critical properties that security analysts actually very care about, right? So robustness, privacy, explainability. So without such guarantee, it's kind of hard to convincing security analysts to use machine learning in real-world security system. The second thing is like security applications introduce some unique challenges. These challenges may break the assumption of existing machine learning models that has been widely used in computer vision or natural language processing. So in many scenarios, simply adapting existing machine learning techniques widely used in those typical application fields may not be truly solve the security problems. So here we need to really diving into the application or really diving into the inside property of security applications and security data and try to design some customized model for specific security applications to make it work. So here are more examples. The first example, of course, we don't know for very large models, even like kind of simple deep learning models, it's kind of hard for us to reason why, right? So it's kind of so in this example, we give a kind of like a neural network model some input software, and then the model tells, okay, hey, this is a malicious software, or this contains some malicious payload, but we don't know why, right? So we don't know the reason why the model makes this decision. So without such an explanation, it's kind of hard for us to build a trust into the model, because I don't understand what's inside the model. I don't know when the model will go wrong, so I don't trust the model. Of course, if the model goes wrong, I don't know why. Since I don't know the reason, it's kind of hard for us to diagnose the error and try to patch the error. As such, I may just simply refuse to use machine learning in my system. The second example also has been widely studied is the robustness issue. Here's another example. Given malware, I inject some adversarial patch. With the adversarial patch, the input could bypass my malware classification and just make the classification model to make some wrong classification. And there are some news to talk about this. Hey, machine learning in recent days is not enough. We're still facing serious robustness problem or robustness concern. Without solving those concerns, it's kind of hard to use those models in practice. The other side of story also give you some examples. The first example is like if you look at the label, right? The data, the label of the labeling process of labeling an image and labeling security data, we can find some difference here. Right? The first thing is like to label some image, we can just find some ordinary people, let them look at image. Within seconds, they can give me the label of this image. But when we try to label some malicious software, right? Let's say this malware, we need expertise to do that. We need hundreds of hours, maybe thousands of hours, static analysis, dynamic analysis. We'll probably need to run this input into some sandbox environment. And then when you set up the environment, we run it, we need to trigger randomability, and then we can see whether this is a malicious software or not. Given all these very hard constraints, so it's very easy for security data to have wrong label. So as a result, like in security data, different from like image or text, we have a rich number of well-labeled data, but in security, we have like a lot of incorrect label and a lot of data we don't even have a label. So it's obvious that if we use typical supervised deep learning model to train such a classifier on these incorrect labels and missing labels, we can expect a model cannot reach a very high performance. So given like all these challenges, like explainability, lack of explainability, robustness, how to handle security specific tasks, and how to handle this in-quality labels, low quality data and labels, given all these challenges, so my research is just try to bridge the gap and try to maximize machine learning capability in cybersecurity. To achieve this goal, during my PhD study and my current research, I made two streams of the research effort. In one stream, I try to strengthen machine learning, just try to make it more expandable and more robust. On the other hand, I try to enrich machine learning for security applications, is that how to build specific model for security tasks and how to handle all those low quality labels and low quality data issues. I think as I highlighted in this research, in this slides, we say like security is kind of a practical domain to some extent. So during my research, I also try to make some real world impact by using my research output. So you can see some of my research highlight that Purple has been utilized by some of my collaborative companies. So especially like this tool has been used by some industrial partners to really try to like do some like, so in this case it's how to do data flow analysis with deep learning, where we can get 10x of acceleration. This case, the second one, the fair work is like how to do flow through account detection in rural economy companies. So there are some like, so that's kind of I'm pretty passionate about that. Is like how can we transform our research product into something that really can be used in the real world, given that we are in this security domain, which is kind of practical domain. So when developing all these techniques, my code technique are, of course, machine learning, but also statistics, because since we are dealing with all these security applications, we want our model to be robust. We want to know when the model goes wrong. So by leveraging some statistic techniques here, we can get some uncertainty of the model we're training, help us better understand when the model make mistake, help us understand the confidence of each prediction. So that's why I feel like statistics is also very important, especially for security application. Of course, I will also use some like traditional techniques, security analysis techniques, especially the program analysis. So these are the core techniques that involved in my research. Due to time limit, of course, I cannot cover all of these works. Therefore, in this talk, I will mainly focus on two lines of work. The first line of work is how to make machine learning model more explainable. The second line of work is how to just handle those low quality data, how to build customized model for those low quality data and low quality labels. Let's start with this explanation stuff. Let me give you one example. First, what is explanation and how to use explanation in security application. So here is an example of machine learning based intrusion detection. So how to do this, right? So to train a model, we first give a set of samples, the network traffic samples. We need to extract some features from this sample, and then these features are just, in this case, are just some summary statistic of each traffic. For example, what is the time step? This is not summary statistic, but is some features related to this traffic. What's the time step? What's its average length of the packet, right? So what's the average inter-arrival time? All those kind of features. And using these feature vectors, we can just plug in a machine learning, deep learning model, train this system, and then the model can tell us whether this input is intrusion or not. So then we talk about explanation. So what is explanation, right? So how can we understand this prediction? So I think the question we're going to ask is the one listed here, right? Given a feature vector as input into our model, the model tells, hey, this is an intrusion. What's the reason of this decision? What are the important features that made the model to make this decision? So there's one, to derive such explanation, there's one widely used method, we call it a Saliency method, which is just simply compute this gradient of the output all the way back to the input. So basically, we compute the gradient of the output with respect to each input feature. We can backpropagate the prediction all the way back to input, and then we just use this gradient, normalize it, and use it as importance score. So basically, if I have a higher gradient, it means, hey, this feature is important. And then from the importance score, we can derive some most important features. In this example, our explanation tells us, hey, these two features are most important. And it's very important, very interesting if we look into these two features, they are average length of send package and average packet sending frequency. So these are indeed some strong indicator, indeed are indicators of some attacks. For example, the DDoS attack. Basically, just try to overview your the target server by sending some small packets with very high frequency. So by looking at these two features, we're able to identify the DDoS attack. So this is just an example of how to draw what is the explanation and how to draw explanation from the model. After the draw the explanation, we can just analyze the explanation and try to understand, hey, whether my model makes the decision based on some correct evidence or some wrong evidence. But although the explanation given by Saliency method are very useful, as I demonstrate here, the downside story is like the explanation methods themselves are vulnerable to attacks. So more specifically, I demonstrate here, what do I mean by attacking an explanation method? So just want to note that this is different from the Adversarial example attack or Adversarial attack. We talk a lot about attacking a target classifier. So here our goal is not the classifier, our goal is the explanation method. So okay, so how to do this attack? basically, similarly, we also add some small perturbation into the input. But the goal of this perturbation is not to modify the output prediction. The goal is to still keep the same prediction, but trick the explanation method to identify some non-important features. So as you can see here, the left and right, the prediction are the same, but the explanation are totally different. So in this case, if our explanation method is under such attack, which means our explanation can be wrong. If we make some decision based on the wrong explanation, it may have some like a negative impact. So for example, if we look at this explanation, we say, hey, the model makes nonsense to me because it just make prediction based on some like very non-related features. In that case, I will not use this model. But the truth is the model indeed learned the right feature, it's just your explanation is wrong. So in this first work, we kind of do an early exploration how to make the Saliency method robust. So to better understand our robust explanation method, we call it dense. Let's recap this attack, right? So how does this attack works? So here is a feature vector indicating the network behavior, and the neural network classified as intrusion. Saliency method will calculate the importance score of each feature. And as I mentioned earlier, an attacker could add a small perturbation to whatever input features, and this input feature does not change the prediction result, but will significantly vary the importance score. So in this case, by adding -1 perturbation to the last feature, we can change the importance score of this feature from 0.85 to 0.4. So this observation actually motivates us, to use a range rather than a single score to represent the feature importance. The intuition is that if we want to enable feature importance of most attack input could fall into this range, then we can say, hey, no matter how you perturb your input, my output explanation is the same. So it's like if all the perturbation, if the importance score of all the perturbation can fall into this range, so it's like my output explanation is at least is robust. But to do this, we know we have a very trivial solution. Is that we set a range to be 0 and 1 for all the features. So since here, as I mentioned earlier, we normalize the importance score to be within 0 and 1. So it's like no matter how you perturb your input, the importance score guaranteed to be within 0 and 1. So by simply set 0 and 1 range for all the features, we can achieve this goal. But obviously, if we do this, it's like for all the features, we have the same importance, which means your explanation is actually useless. So how can we tell which feature is more important from a set of such ranges, right? So with this in mind, so I think our goal becomes this, is that still we want to use a range, but we want this range to be tight enough to capture the feature importance. And we also want this range to cover the importance scores of most attack inputs. So basically, it's like we want to draw a balance between your explainability and the utility of the explanation and the robustness of the explanation. To satisfy this design principle, we design our method as follows. First, to ensure our range could cover the importance scores of most attack, we design a method to perturb different subsets of features. As I will discuss later, our feature perturbation method could retain the prediction and at the same time obtain the maximum perturbation that could be added to the features. So basically, we try to design a method to mimic all the attack perturbations. And then by adding all this perturbation to the original input, we could get a set of perturbed input that, as I mentioned earlier, could mimic the attack with largest perturbation that cover most attacks. And then with all these perturbed inputs, we then compute their feature importance score with existing Saliency method and find the range for each feature. Since the range captures the feature importance of all the attacks, so it's very so since the range captures the feature importance of most of the attacks, so it's very likely to be robust even under attack. So finally, use this range, we can use this. Finally, I will also discuss, how to transform these ranges into one score for each feature, and then use that feature as the importance. Sorry, into one score of the feature, and then use that score as the final importance of each feature in this input. So let me first introduce our how to generate the perturbation. In this case, we call our perturbed input as decoys. So idea is also kind of similar. It's like idea is quite simple. It's like, remember, we want to keep the prediction of the perturbed sample, which is decoy in our case. To do that, we want the decoy sample and original input to have similar hidden layer representations. If we have a similar hidden layer representation, of course, we can keep the same prediction. But at the same time, we also want the perturbation to be as large as possible. So we can construct such an objective function. It's like we add some perturbations into some features within input. And we want to maximize these perturbations. But at the same time, we want to keep the hidden layer representation of the original sample and the perturbed sample almost the same. So by solving this objective function, we can get some perturbations, and then by adding this perturbation to the input, we can get the decoy that enable the largest input perturbation, but still keep the same prediction result. And in our case, we generate different decoys by perturbing different features. So basically, in this demonstration, first decoy will perturb the first and the third feature. The second decoy will perturb the first and last features, and so on and so forth. So we can generate a set of decoys. So this set of decoys could mimic most of the attacks and with the largest perturbation. So we cannot say they are like strong attacks, but at least we can cover most of the attack spaces within this set of decoys. And then the second question is like, how can we generate a single important score for our original input by using this set of decoys, right? So the first step is like we need some scores. So we use existing saliency method, the gradient-based method, to generate the important score for each decoy. And then we need to compute the range, which basically maximum and minimum. And then the final step is how to get the final score from this range. Right? There are multiple choices. The first, you can use the minimal, you can use the maximal, you can use the mean, you can use whatever interval within this range. But what we do is that we use the diff between the maximal and the minimal score as our final score, as I demonstrate here. The reason we are doing this is like this diff between these two gradients is actually try to mimic the second order hashing information of the original input feature. So basically, theoretically, we can show that this range and this range and the hashing of the original feature are actually bounded. So which means if we use this diff as the final score, it could indeed capture the importance information of your original feature. So this kind of resolve the question we asked. So how can we get a score from the range that could indeed capture the feature importance? The simple solution is just use their diff because it could capture the hashing matrix information. So with that, that's basically our technique. So basically 2 steps. The first is generate decoys. The second is get a score, important score from the decoy samples. And then we do some experiment here. So here is a qualitative study. So basically, the first and 2 columns are the important score of the original sample and the sample under attack by using some existing saliency method. As we can say, like, just after the attack, the importance score switch totally. Basically, the importance score, the feature importance given by an existing method before and after attack are entirely different. But if we use our method, it's obviously more robust. And then we also do some quantitative evaluation. Basically, we just design this sensitivity score. It's just the difference of the importance score given by one method before and after the perturbation. And this score is the lower the better. So we can say like by using our method on all the existing mainstreaming gradient-based explanation method, it could reduce the score by a very large margin, which means it indeed makes the explanation more robust. And finally, we also show some theoretical, we also do some theoretical analysis and show theoretically, if we use a ReLU network, feed-forward network with some ReLU activation functions, this feed-forward network include both MLP and a convolutional network. So our method is actually more robust than existing Saliency method. And then we jump to the second work. So basically, the robust Saliency, probably I can post here to say if there are any questions regarding the first work. Okay, maybe no. So yeah, I'll just continue. And then this second work is about how to generalize this Saliency method to more scenarios. Because like in security domain, we are dealing with sequential models a lot, right? So we're dealing with recurrent networks instead of all these feed-forward networks. But one can show that the Saliency method cannot retain its performance in this sequential network because of gradient segregation or gradient vanish. And the second thing is that sometimes we don't have the model architecture. Sometimes we are dealing with black box setup where we do not have the model. So how to if we do not have the model internal, of course we cannot compute gradient, and then we cannot use the Saliency method. So my second exploration is actually talk about how to do the explanation for black box sequential model. I think for the interest of time, I will not dive into details. I can basically explain to you the high-level idea of my work by using this demo. So this is like a binary function style application. If you don't understand this application, you can just take it something like this. We train a model, the model takes in a sequence of number, and then the model tries to identify the most important or most useful number within this sequence. So that's all about this model. So basically, input is a sequence, and output identify one position within this with input sequence. And then the goal here for explanation is, for example, in this case, the model taking in this sequence of numbers, and then it identifies, okay, 55 is the one I want. The explanation here is try to understand, okay, why 55? Why not C3? Why not 5D? To do this explanation, what we do is like we try to mimic, and in this figure, I use this curve to represent the decision boundary of the neural network model. And this is the sample of interest. To do the explanation, what we try to do is we try to just approximate this decision boundary with some explainable models. In this case, it's linear mixture linear regressions. Is that we train multiple linear models to fit the local curve of these very complicated decision boundaries, and then we try to draw the explanation from this linear model, because we know the linear model is explainable. But if we use one simple linear model, since our decision boundary is highly nonlinear, you may not enable a very accurate approximation. In that case, the explanation won't be very accurate neither. So that's why we use a mixture linear model to do the approximation. And of course, we add some regulation term to capture the sequential dependency within the input. And after fitting this model, we just explain this linear model, we can draw the explanation we want. So that's basically a very high-level introduction of this work. And I think not only this work actually won the best paper award from CCS. I think the reason why it, maybe it's just my guess, why it won the best paper award is not only because this new explanation method, it also we actually study what are the utility of our explanation. So here I just give you some like a very high level, like a very high level and brief introduction about all these utilities. To give you kind of understanding how can we use explanation, right? So the first thing is like we know that deep learning models sometimes, most of cases, deep learning models has done better job than human on some tasks. For example, the task we show here and some other image classification tasks, all those tasks. So if the model actually do a better job than human, which means the model should learn some new knowledge. And then by introduce the prediction given by the model, we can try to understand, what are the new knowledge learned by the model, whether this new knowledge makes sense or not. So in this example, give some case study to show that in our specific application, explanation can help us derive such new knowledge. That's the first utility of this explanation. The second utility is like, as I mentioned earlier, if our model goes wrong, by explaining those errors, we can use those errors to patch our model. So here we also have done some simple experiment or simple attempts in this work to try to say, hey, how can we use the explanation to do the patch? So what are the utility of using explanation doing patch? So that was back into 2018. So, and our patching was kind of naive. We just do some manipulation and do some data augmentation based on our explanation. But I think recent days with all this large language model has billions of parameters, which means if the model goes wrong, retraining the model from scratch is very gonna be cost a lot of money, a lot of resources. So I think under this scenario or under this context, fine-tuning or explanation-guided target fine-tuning should be more interesting. So that's because previous what we did in 2018, we just do 2 layers of recurrent network. Training that model is very simple. You can take probably just 1 hour, you can retrain whole model. So doing some target patching on that model, recently, if we look back doing target patching on those models, it's not that useful in the sense retraining is very simple, right? But if we do retraining on large language model, which takes maybe months of training, in that case, patching and fine-tuning is more important and more useful. So that's also something I'm looking into right now. And then I will also want to show you some cases about extending my explanation technique to deep reinforcement learning policies. Also very hot topic in machine learning is that reinforcement learning is just, in this case, it's a game example. It's a reinforcement learning agent control the robots in this game. So this game is kind of like American football, where we have 2 players. The red player tries to cross the line behind the green player, and then this green player tries to block the red player. And this is a game episode I show you. In this example, the red player actually lose the game. And then we want to explain, okay, why the red player lose the game, why the green player win the game. What are the important moves? What are the important steps? So here I show a video demo example. So basically, the color bar under the video shows the important of each snapshot. So as we can play the video, we can say, hey, the first fields are not that important. And then when 2 agents interact with each other, it becomes more and more important. And then when the right agent fall into a ground, it's another line of important steps. So basically, the explanation tells us, hey, why the right agent lose? Because the gray agent block the right agent and the right agent fall into the ground. So this kind of intuitive, but also match our human intuition. So that's a demonstration about the explanation we have done on the deep reinforcement learning models. And recently, we have extended this work to try to explain some more complicated games, for example, the poker game, Texas Hold'em, and even the Go game. So of course, we can still do the patching, right? So after we identify the most important time steps, we can just patch the agent and try to, basically means, in this case, the right agent loses the game, which means at these important time steps I show you in the last slides, the right agent took some wrong action. So patching the agent, the idea is also kind of simple. Can we let the agent to establish some right action or correct action on those important time steps? If we correct the agent's action on those time steps, can we lead the agent to win the game instead of losing the game? So here is a demonstration before and after patching. Is that we just apply the patching at a few time steps, the important time step we identified earlier, and then you can see our agent was able to, the right agent was able to just bypass the block and then just win the game. So this is a demonstration of the patching strategy we have done on the reinforced learning kind of work. So this basically concludes my previous work about the explanation. So basically, we have done three things. The first thing is just how to make the explanation more robust. We can say an ensemble learning method can help us do that. The second thing is like we try to design some statistical model to approximate the neural network model locally, and then try to draw some explanations. The first thing we demonstrate explanation can help us discover new knowledge and even patch the model error. So that's basically the first line of my work, conclude the explanation. I also have done a lot of things regarding the how to robustify a machine learning model. Due to time limit, I cannot cover this topic, maybe next time. And then I will briefly introduce one work here. We have done also some works. This work recently has been accepted by OCA. We submit to the first work, submit to CSS, and then got rejected, and then we resubmit. And then we have done, we are doing some new things, leveraging large language model to handle all those challenges. But here I use this NDSS work as a demonstration because the reason is it has been utilized in some products, so I feel it's actually useful. And let's look at the problem. I briefly mentioned the problem earlier. It's like incorrect labels and missing labels are very common in security data. But then what are the incorrect labels? What are the missing labels, right? So what format of incorrect labels we are facing? So here we dive into more detail and then say what are those, how those labels looks like. The first thing we say or we discover is coarse-grained label, which means, for example, in malware classification, we can mistakenly group several malware families into one giant class. So here is a demonstration. The second, for example, let's say if we upload one kind of like a malware payload into a virus total, and different vendors can give us, all those vendors tell us this is a malware, but at different granularity level. For example, the first thing just tell us, okay, hey, this is malicious, and the second one tell us this is a Windows downloader malware, and then only the Microsoft can tell us this is a Trojan malware. So coarse-grained label are very common in malware classification, right? And then the second thing, of course, is missing label. Because of high labeling cost, we cannot get a lot of labels we cannot label all the malware samples. And then our goal in this work is try to recover the true and the Fain-grained clustering structures given these coarse-grained labels and the missing labels. The high-level idea to do this, actually, there are some existing work, right? First, we can just ignore all the labels and do unsupervised learning. Of course, since we don't have a label, sometimes it just, most of the time, it cannot work pretty well. And then we can also try some semi-supervised learning or supervised learning method. But all these methods, their underlying assumption is like, well, we don't have coarse-grained label, and we need at least one cluster or one class has at least one label data. So that's why like some mainstreaming existing techniques doesn't work. So that's why motivate us to design our own technique. But this was back in 2021. At that time, we don't have all those fancy attention-based pre-trained model. So, and then we don't have all those zero-shot learning models. So that's why we designed this. But recently, maybe with zero-shot learning models, they can do better. So the high-level idea is just we try to draw some useful information. First is that since we don't have enough label, the first thing we do is that we run some cluster method on top of our model, and then still try to cluster the data into different clusters. And then based on this cluster assignment, we train a contrastive learning model, which just try to map all this input data into some hidden representation. Within hidden representation, we want some property. The first property, of course, we want sample from the same class to be close to each other, and sample from different classes to be far from each other. And we also want this hidden representation. The distance metric can be measured. So if we can measure the distance metric with, say, some distance measure, like Euclidean distance, then based on this hidden space, we can easily run some clustering method and then try to and then get the final cluster result. So that's kind of like our goal of doing this contrastive learning. It just preserve the pairwise relationship of the input sample and make the sample more separable, and then just we want to preserve the distance measure. Finally, we can just, with this very nice property on this hidden space, we can just apply a k-means method, and then we can just get the final result. So the high-level idea is that first, try to leverage some unsupervised learning to draw some useful information from the data, since our labels are corrupted. And then use those information, try to learn some very nice representation of your input data. The final step is very simple, just run some clustering method in the hidden representation. And then we have done some experiments to compare our method with different type of method. First, we compare our method with some clustering method. As we can see very clearly, by assembling multiple clustering method and utilizing the label information, our method significantly outperform existing unsupervised learning method. We also compare our method with some supervised learning method. Still, we can say it perform better than the existing method, especially when the problem getting harder. It's like in this example, we have 9 classes in total. If we mark 7 of the classes as unlabeled data, we can see most of existing work method no longer work, but our method still can draw a decent performance. And then we just apply it to some real-world application, showing it work, and you can discover some unseen behaviors. I'll just skip this. So finally, here's one slide again, summarize my work. And then I can discuss some of my future works, but that was like 1 year ago. So right now I'm doing all these things. So the first direction is like what we have done before only focus on this incorrect label and missing labels. But we know security data have a lot of other problems. For example, concept drifting. We have a lot of class imbalance. We have low quality data. So all these individual problems are not unique to security application. In vision, in language application, we all have these problems, and there are a lot of methods try to solve each problem individually. But when combine all those things together, it's kind of unique for security applications. So it's like in security data, we can see all these problems happens together. And we have done a recent study to just show if we apply the existing methods for handling incorrect label and to a data set with class imbalance, most of existing methods no longer work. So which means there are indeed some challenge here is how to design effective method to handle all these problem data and label problems at the same time. So maybe the potential techniques, we can leverage some contrastive learning, we can leverage some generative model, help us do data augmentations. That's one set of stories, how to make our machine learning model do better on representing security data under all this data and label issues. The second set of stories is like how can we use machine learning to model more security tasks, right? So currently, if we are only say, hey, I'm doing classification, doing clustering, these are kind of limited because in security application, there are so many other tasks. For example, we do some vulnerability discovery, vulnerability deportation, even we want to patch the vulnerability. These are more like sequential decision making. It's like I'm not making one simple classification or clustering decision. I'm actually need to make a sequence of decisions to achieve my final goal. So how to do this, right? So a very promising direction is try to use some reinforcement learning techniques. We can leverage reinforcement learning to design specific system or techniques to help us to handle more complicated security applications. Of course, when doing this, we need the model. Whatever model we develop, we want it to be explainable and we want it to be robust. So that's basically my kind of like my short-term research vision about how we should proceed about using machine learning in more security applications. So basically just how to draw better representation and how to do better decision making. And of course, large language model can fall into this category. Is that we can leverage those great models to help us to draw better representation. And then in the long run, what I have told you are mainly focused on the modeling and the evaluation step. And of course, we have many other, if we look at the machine learning life cycle or pipeline, we have many other type steps. For example, how to collect the data, how to deploy a model, how to monitor and maintain the model. So my long-term research is help improve machine learning in security along its whole life cycle. One very interesting topic I'm also looking into is how to enable better coordination between human and machine learning. Right. So currently, most of technique in security are human heuristic based. How can we better encode AI together with those heuristic models is very interesting. And this summarizes kind of my research. My core is in machine learning and security. Of course, I'm looking into some other application domain as well. So that's basically summarize my talk. And thank you so much for your attention. Finally, I want to say, like, since I will be joining Purdue as an assistant professor, and I will working on all this, at least this short-term research. I'm working on all this topic right now. So I'm very eager to work with some young brilliant students. And if you're interested in all these topics, you can reach out to me through either my Berkeley email or my Gmail. We can discuss some potential collaborations as research interns in all possible ways, right? Research intern, waiting scholar, and of course, PhD students, graduate students. So I'm very eager to work with young talent here, and let's together make machine learning more useful in security applications. Yeah, that's basically conclude my talk. Now I'm saying we probably get 2 more minutes for the questions.